you. So can you hear me with the mic? It's okay. Yeah, the back. Okay, perfect. So first, I must say that it's of course an immense pleasure to be here. I try to remember when was the first time I saw Asa, and I admit I cannot. It seems that I've known him, you know, forever. So the first documented time for me that I can really pinpoint was this conference in Trieste, which is relatively recent, 2002. And then, of course, Asa is responsible for something which is very important for me. He was the person who organized my first visit to Israel. And he invited me to the Technion, and then I could visit also, of course, many other places. So it was a very, very fond memory. And Asa was a fantastic host during this week. It was absolutely incredible. And I think it reflects all the things that have been said about it. Before I go to physics per se, I wanted to abound in a sense that was already said. Asa, like many good physical theories, is totally invariant by translation in time. And here is a photograph coming from Trieste, where you see Asa. And here is a photograph, or several photographs, of a workshop in Technion in 2009. For today, you have the present, you don't need a photograph, you have Asa. And you can see that, well noticed, very little change actually in the person. For other characters in the photo have changed, gone to more S-wave symmetry. For people who have doubts, this is Duncan Aldane, this is not Duncan Aldane. This is Martin Reiter. So my case rests, and I stand that Asa is invariant by translation. Concerning the topical of this, my talk, it was really a no-brainer, because in addition of many, many nice paper, and of course many, many discussion, Asa likes to discuss, Asa likes bosons. We had several discussions on hardcore bosons, which I really enjoyed, but of course Asa has also done a contribution, major contribution in quantum magnetism, and the author of a fantastic book on the subject, so I could not resist, of course, telling you a little bit in these common words, telling you about some quantum magnetism problems. So forget about ITC, metals, whatever. I'm talking during this whole session on insulators, so just quantum magnets. And I will try to show you how they can be used as quantum simulators. Now, of course, this is a talk for the 60 years birthday. I was shocked when I received the message from Netanel, because I really cannot imagine Asa being 60. But given that it's a talk for 60th birthday, maybe I should put the title like this, so that everybody can see it. No, so then go back to the more serious stuff. Okay. So more seriously, what I'm going to tell you is a long effort that we have in the group, and which stemmed from works with Chitra and Svelik long time ago. And at the moment, they were mostly carried out on the theoretical side with a very smart postdoc who just left my group to go back to Japan, Shunsuke Furuya, a graduate student, Emmanuel Koira, and of course there are long-standing collaborations with Corina Collat, who is at Bonn University, and also a former grad student of the group, Pierre Wu. And we were really fortunate to have collaboration with many, many theoretical groups. Some of the people are in the audience here, but also many experimental groups, in particular on NMR, the group of Claude Berthier, and Neutron with Christian Rueg and André Zellur. Okay, so what is this about? Let's imagine I would like to work about bosons. I would like to understand something about bosons, and we have many remarkable systems of bosons. Maybe I will stand on the other side. And these are, of course, incondense matter, helium-4, exciton, polariton, superconducting states, you name it. Of course, we have cold atoms, which are proven to be a major player in the field. But in many of these systems, the question of homogeneity, control of parameter, is an issue. And the point is, could we complement, of course, the list of all this wonderful system by an additional system which suffer less from questions of homogeneity, and especially the question of control parameters. And what I would like to show you is that one can think about magnetic insulators as a way to do that, and therefore use them as something people have started to call a quantum simulator. The name quantum simulator pops up in many situations, but actually look at magnets not as trying to understand the magnetic properties, but as trying to simulate the behavior of itinerant bosons. And the idea of a quantum simulator is, of course, very old, and basically what it means is that it's an experimental system, but which is a faithful realization of a model system that we would like to have, and therefore, by just doing the experiment, we can read the answer of the theoretical Hamiltonian or whatever that we would like to. So let me try to explain on as simple example as I can this thing, and it's of course an idea which is not new. We implemented for dimers with Alexei Zvelik now in the last century, let's say it that way. Let's assume that I start from a system which is a simple Heisenberg Hamiltonian. So again, charge is out of the picture. I have only the spin 1/2 degree of freedom on each side. And let's assume I have very strong antiferromagnetic exchange on the yellow rungs. And for the moment, let me ignore completely the white rungs. Then you all know how to diagonalize this problem. You get a singlet state, which is separated by a gap from a triply degenerate triplet state. Now, imagine you put a magnetic field, then the singlet will not be affected, the triplet will split, and at some point, one of the triplet will touch the singlet. And if you do this, you can, and ignore the higher state, you can do a mapping by saying that the singlet is like the absence of a boson on a rung, and the triplet is like the presence of a boson on a rung. And trust me on that, it satisfies all the nice combination relation that it needs to satisfy. So you replace, in a way, your spin model by a model where bosons live on the rungs. And of course, because now of the residual exchange that exists, that I ignored so far, this boson can hop from rung to rung. So this problem is a faithful realization of an itinerant boson problem, of hardcore bosons, because you cannot put two bosons on the same rung. It has no meaning. It means the rung is occupied by a triplet. And therefore, you see that by using the magnetic field, you can change the number of triplets, meaning the magnetic field is acting as a chemical potential for the particles, the pseudo-particle that we know. And of course, this is not something that is new in itself. This is the old mapping of spin 1/2 to hardcore boson by Matsubara and Matsuda. Here it's done for dimers, which is a little bit more sophisticated, but the idea is essentially the same. The exchange, XY exchange, will provide kinetic energy for the boson. The JZ exchange will provide the nearest neighbor interaction for the bosons. And of course, there is also the on-site infinite repulsion. The problem is hardcore bosons. And as I said, the magnetic field is a chemical potential. So it's like doping a system, except you can do it in 3D. You're not limited to 2D system like with most gate doping that exists for real metallic or itinerant material. Here you can do it in 3D, and you can go from an empty band of boson to a completely filled band of boson. So you're not doping with 10% doping, you're doping from 0 to 1. So this is, if you want, a very convenient type of system to look at. Why it was not acted upon and used before is a very simple limitation, which most antiferromagnetic exchange are of the order of, let's say, 1000 Kelvin, which means that if you want to manipulate this system with a magnetic field, you would need a magnetic field of 1000 Tesla. And that's not really a human magnetic field. So the thing which made the manipulation of this system and the use of this system as quantum simulator possible is the fact that people could synthesize compounds with exchange of the order of 10 Kelvin, which means you can manipulate them with fields of the order of 10 Tesla. It might be 20, it might be 30, but as we saw in the previous session, up to 90 Tesla is not a big problem. It's starts to be a big problem, and let's say up to 20 Tesla is not a major problem. So this can be done. So not only you can dope them, you can use them, but you can probe them very efficiently. The magnetization gives you the number of bosons. The magnetic field acts as a chemical potential, so you can do extremely fine sweeping through quantum critical points. And of course, neutrons and NMR are typical probes. It's not the only one. There is electron spin resonance. There are many other probes that one can use, Raman and so on and so forth. But for example, these two probes typically measure the spin-spin correlation function at different point and different time, at least for the neutrons. And this translates directly for the equivalent bosons onto density-density correlation function. And the S plus, S minus spin correlation function gives you directly the single particle correlation function for the boson. So you have very naturally probes that probe the superfluidity of the bosons and the density order of the bosons. Okay. So with that, one could do a certain number of things. I will, of course, not have the time to describe all of them. The first thing, you have bosons, so it's very natural to study Bose-Einstein condensation, and actually, these were materials in which Bose-Einstein condensation was studied in 3D and 2D. There are reviews here, and I refer to you to this for the Bose-Einstein condensation. I will not have time to say much more. In 1D, you know that we don't have a Bose-Einstein condensate, but in 1D, we have a Tomonaga-Luttinger liquid, and as Duncan told us, we can compute all the correlation function we want using field theory. And therefore, one question one can ask is, can we test quantitatively this Tomonaga-Luttinger liquid theory on these systems? Here is the experimental compound. It's a ladder compound which is called BPCB, with very strong exchange between this copper side, weaker exchange along this direction, about 12 Kelvin here, 3 Kelvin along the legs, an extremely small exchange between the ladders of the order of 50 millikelvin. So you have a wide regime in which these compounds are in 1D regime. And lo and behold, I won't detail it too much, again, I give you reference here. Lo and behold, you can make a very detailed comparison because you know the microscopic Hamiltonian. That's the main difference. When we deal with charge system, we don't know very well the screen-Coulomb interaction. We modelize it by a Hubbard U and the nearest neighbor V and whatever, but we don't really know the microscopic Hamiltonian. For these problems, because the charge are motionless, you can compute, not directly, but you can measure or compute indirectly the exchange constant, so you really have the Hamiltonian, and you can make a quantitative prediction of what you should see with no adjustable parameter. And just as an example, here is the relaxation time in nuclear magnetic resonance, the so-called 1/T1, as a function of the magnetic field. This is about 7 Tesla, this is about 13 Tesla. And you see, this is the data points taken by Martin Klenchuk and a group of Claude Berthier and Mladen Orbatich. And the data points are here. And the red curve is the theoretical prediction based on the Tomonaga-Luttinger liquid theory without any adjustable parameter. So it's not only that the shape agrees, but the amplitude agrees perfectly. So I would say that's the first time that one could check quantitatively, not just that there is an exponent or something like this, the accuracy of this theory. Let me skip that because I want to mention other things. Okay, so these two examples show that they are good quantum simulators. So before I go to more theoretical issues, you could say, what good is a quantum simulator if you only test it to theory for which you know the answer? So let me show you one case where we could use it for testing something for which we do not necessarily know the answer. And this is the problem of disordered bosons. And you all know that the problem of disordered bosons lead to phases which are insulating. This is the Bose glass phase that Hein Schulz and myself and Matthew and collaborators were playing with definitely in the last century. And this, the combination of disorder and the bosonic nature of the particles give a possible transition between a superfluid phase, which is delocalized, and a localized phase due to disorder. So there are good theories to compute a certain number of the properties of this system, but getting a full description of the phases is not so easy. And observing it, especially in 1D, is not so easy. So here is a recent example on which I don't want to go too much in detail of the group of Florence, the group of Massimo and Buscio in Florence, where they used cold atoms to test for this by varying the interaction between the bosons and the strength of disorder. Actually, it's a quasi-periodic potential, but I don't want to discuss that. And where they see very clearly a phase which is coherent. This is the width of the single particle coherence peak. So let's call it the superfluid phase here, which is surrounded by a phase in which superfluidity is destroyed, and this phase can be interpreted as the Bose-Glass. Now, in magnetic system, it sounds like the ideal system to test for disorder. Why? Because the Bose-Glass is a compressible insulator, so you need to test for its compressibility, dm dmu, but this is just dm/dh, which is easy to measure. And then if you want to test for the superfluid order parameter, as we discussed before, neutron scattering experiment can give you the corresponding information. So there has been an experimental effort, which has been quite strong, to try to see this phase. So here are a couple of experiments. This is something done by Andrei Zeludev and Louis Pierre in ETH and Grenoble, where this is the curve M of H. This is the pristine sample without disorder. The disordering is produced by alloying far from the copper side, so far from the spin 1/2. So it produces random exchange between the spins. You see that when you put disorder, there is a region where the compressibility becomes finite. This curve is the derivative dm/dh. But at the same time, in the same sample, if you look at the peak in neutrons, there is no peak that appears, and therefore you could say that this region is most likely in the Bose-Glass phase. There are some problems with this material, so people tried other materials. Here's the thallium copper chloride, where again, if you look at the temperature magnetic field phase diagram, the pristine sample show relation between temperature and magnetic field, which has the power law characteristic of a Bose-Einstein condensation. Once there is alloying in the material, you see that the exponent changed dramatically, and again, this has been interpreted as Bose-Glass phase. A more recent experiment is done with DTN, spin-1 system, where again, because of the variation of the exponent and the comparison with QMC calculation, this is the Los Alamos group with theoretical input from Tommaso Roskilde. They want to interpret the region which exists here and there as a Bose-Glass phase. Now, interpreting the existence of a phase by looking at the exponent of the transition is quite complicated. So it would be much better to have direct evidence. This is not yet out. One of the reasons is that many of these compounds lose the transition in zero field when they are disordered. So one very promising compound is this latter compound that I showed you before, which has been doped. Here is the various colors of the material when you go from full bromine to a full chlorine system. And hopefully, now the phase diagram of these two extreme cases have been mapped. And normally, now by putting a few percent of disorder, one can now try to analyze this compound and see if it has Bose-Glass. So I don't have the answer for this compound, it's not yet out. But that's one example where we can go and try to read directly on the experiment the answer on a system of disordered bosons. I would like to use the time in 5 minutes or so that I have left to go on a more theoretical ground and tell, okay, we have this fantastic quantum simulator, so that's great, the theorists can sleep and has nothing left to do. And actually it's not true for a very simple reason, that we had fantastic theories to deal with quantum magnetism, but for, I would say, the old magnets. Magnets with exchange which were of the order of 1000 Kelvin. Here we need human value for J. What I call human value, I mean values of the order of 10 Kelvin or so that can be manipulated by a magnetic field. Which means, as a corollary, that when you do an experiment, J is not so large compared to the temperature. Which means that most of the use that we did before of field theory and so on and so forth has now a much more limited range. And we have been relying on this asymptotic analysis very much. But now, in order to really understand these experiments, we need a quantitative computation of the correlation function. We cannot say when T over J is a factor of 10 to the minus 4, we can use field theory or Tomonaga-Luttinger liquid or so on and so forth, because this regime will be very hard to reach. And the question is how to get this. So fortunately, in the recent years, there were important development on the numerical side, on the method in particular invented by Steve White, which is the Giamarchi, density matrix renormalization group. And this method is now allowing to do finite time, finite temperature correlation functions. And I just want to flash a couple of results on what one can do by using this method and potentially combining it with the field theory. So the message, the take-home message of this part is that now we can quantitatively compute for simple 1D system the finite Q, finite omega, finite temperature correlation function, which is, I would say, for me, quite remarkable. And 10 years ago, this was essentially impossible. Here is an example. This is a compound called DIMPI, which was measured by neutrons at the Bolshevik Institute by Andrei Ziludev. And people knew that this compound had a ladder structure, but they didn't know what was the exchange J along the rung and along the legs. And it was difficult to use the standard method, which is to extract them from magnetization, because the critical fields of this material are a little bit high. They are of the order of 40 Tesla, so it made it impractical. But they had neutron scattering experiments, so using the Giamarchi, we could compute fully the correlation function. So this is as a function of Q and omega, the structure factor, so the S plus, S minus correlation function. Since it's a ladder, there is a symmetric and an anti-symmetric mode. Q equals 0 along the run, or Q equals pi along the run. And these are the two plots here. This is Q equals pi, this is Q equals 0. And essentially, we could compare with the neutron that was measured at 0 magnetic field. Then we let the parameters J parallel and J perp free, up to the point where we got matching with the experiment.
This is a few coupled ladders? Or?
So the coupling between the ladders is extremely weak. It's, let's say, to give a number, 50 millikelvin. So if you're at a temperature of 1 Kelvin, which for the neutrons here, the scale is milli-electron volts. So the lower they can go here is 0.2, is higher than the temperature. So the temperature is not affecting the neutron spectrum, but it's completely killing the coupling between the ladders. So you can really view the neutron spectrum as fully 1D.
Yeah, simulation is just one.
Simulation is just one ladder. So what is the, okay, can someone want to take the bet on what is the calculation and what is the measurement? So the points are the measurement, and the whole rest of the figure is the calculation. So we beat the neutrons in resolution. No, I'm not joking. We had to broaden the spectrum to match with the neutrons. But then, by doing this, we could get the J parallel, J perp, and then play the same game. This system is coupled by an interladder coupling, so let's predict the TC, and here is the curve that is coming from the prediction using the parameters that were determined, and these are data coming from specific heat measurements, so you see that this has serious predictive value. Yes?
So what is the difference between the one before, the data, between A and B?
So this one is Q equal pi transversely to the ladder, and this is Q equals 0 transversely to the ladder. So this one is looking at the correlation of S1 minus S2 on rung 0 with S1 minus S2 on rung R, and the Fourier transform of this, while this one is looking at the correlation of S1 plus S2 on rung 0 with S1 plus S2 on rung R. neutron is working in Fourier space, so you can access selectively this. Okay. The difference between this one, this compound, and the one I showed before, the BPCB was a strong run compound, where this was about 12 Kelvin and 3 Kelvin along the legs. DIMP is the opposite. It's about 12 Kelvin along the legs and only 3 Kelvin on the other direction. So it's totally different. Okay. So it works. Here is, for example, the full spectra computed for 2 coupled chains as a function of the strength of the coupling. So if the coupling is 0, then I get 2 uncoupled chains, and the 2 spectra are the same in the Q parallel equal pi and the Q parallel equal 0. Q perp equal pi and Q perp equal 0. But as the coupling between the chain increases, you see that gaps appear in the spectrum. And if you want, this is DIMP and this is BPCB, where you get a triplet which is dispersing in the system. Just to show you that we can do that, we can again compare with neutron scattering experiment. Here is a comparison between spectrum taken in neutrons in DIMP and the corresponding calculation with the MRG. So this works very well, and this allows to identify physical phenomena like, for example, bound state of magnons that were predicted long time ago, but could never be observed because we never know where to look quantitatively in the phase diagram. I want to finish with a very recent work on NMR, because we have the same effects on the NMR. We all know and love the famous formula for the NMR, which says that the relaxation time is the local spin-spin correlation function at the NMR frequency, essentially 0, which means that it's the sum over all Q of this correlation function. And usually, because we say, oh, there are few low energy modes, we approximate this sum by Q equals 0 plus Q equals pi, or whatever are the low energy modes. Well, again, if the temperature is comparable to J, we cannot make this approximation. So, for example, if I use this approximation, I can get from Tomonaga-Luttinger liquid theory a power law dependence for the NMR, and this is what was used in the previous NMR comparison that I showed you, because the temperature here was still low enough. Now, I can also compute this correlation directly from the numerics. And then here is, for example, some example of the results. Here is, as a function of the temperature normalized as J, sorry for that, the NMR relaxation rate, let's say. So the data points are for, so this is a spin chain, a single spin chain, with data at various magnetic fields. So one of them is the critical field, so just the field at which the chain will be fully saturated in magnetization. This is some intermediate magnetic field, and the green is zero magnetic field. So for zero magnetic field, we know that the NMR rate should go essentially to a constant if one ignores logarithmic corrections that I don't want to discuss here, and the numerics is telling you that. For a field which is intermediate, which is the red curve, we know that asymptotically we should recover the Luttinger liquid result, Tomonaga-Luttinger liquid result, which is this power with this amplitude. There is no adjustable parameter here. We know both the power and the amplitude. And you see that the data is doing this, but you see that very soon, at 0.2, 0.3 of J, there are strong deviations in the exact computed NMR signal compared to the asymptotic formula. So if you try to fit an experiment in this regime by using the asymptotics, you get it completely wrong. So for these materials, having the possibility to get quantitative prediction is, of course, very useful, because again, for most of the experiments now, the temperature will be a sizable fraction of the exchange, which was not the case when the exchange was of the order of 1000 Kelvin. For the critical point, it works extremely well, up to very large temperature, and this curve here is just a fit with the power law of 1 over square root of t that was predicted long time ago by Senthil, Shankar, and Subir. And not only the power law works, But if you try to measure the amplitude, you can map it to a free fermion model, and then you can see that the numerics and the prediction of the free fermion model work very well at the critical. Okay, my time is essentially up, so I will conclude. And again, I wanted to show you that localized spin system can be used as quantum simulator, and it worked for a lot of physical phenomena, Bose-Einstein condensation, testing the Tomonaga-Luttinger liquid, dirty boson, it's on its way, but that's, I think, one of the most interesting applications. I didn't talk about the hole in the TJ model, but you can also use this system for that. There are excellent experimental realizations, and one thing which is important at the theoretical level is now, in a pure 1D system, we have the power to do quantitative calculation of correlations at finite temperature, finite frequency, finite moment. There are, of course, many perspectives. We need to move now to higher dimensions. So how do we couple the chains? What is the dimensional crossover in these materials between 1D and more than 1D? What are the behavior close to quantum critical points? If the material is purely 1D, we know how to do, but as soon as there is a degree of 3D coupling, close to the quantum critical point, the material will have a dimensional crossover in addition. And of course, we would like more complicated structure, frustration, Jaruzinski-Moria term, impurities and doping. And on that I stop, and I show you, of course, the most important slide.
Can you show again the magnon-magnon coupling data and explain how do you know there is coupling in the, what is the data tell
This
you?
one?
I think it was
This one. Yeah, okay. So this is, let's take this spectrum. This is the anti-symmetric in the perpendicular direction. This is the symmetric in the perpendicular direction. The bottom of this, we know from theoretical grounds that it's produced by the bound state of two magnons. Now, this is only visible in the symmetric part of the spectrum, not the anti-symmetric, but the neutrons don't care. They measure on one spin, which means they average these two. So it means that in the neutron data, one had to search for a trace of this. And it's not so easy because you get a continuum and so on and so forth. So by having the quantitative prediction, we could tell them where to look, and they could improve the quality of the data. They also, of course, add on their side a lot of progress in resolution and their own tricks to improve the data. But then they could look at this and see this part, which is the magnon-magnon bounce.
What does it mean magnon-magnon on a chain? For me, two-particle bound state is a motion like this.
Well, even on a chain, either particle can go away or they
So
don't.
what's bound about it? If two particles go far from each other.
Then they are not bound. They can go together.
Stay close to each other.
When you dance with someone, you know, you can move very far but stay close. So then it's a bound state. Yeah.
Yeah, I wanted to ask what plays the role of the disorder of the, if you want to map it to charged bosons, you would think of a random potential.
Yeah, so here, let me try to go back to the picture I showed of this material. So the spins are carried by the polar side here, and they are in the bridge. There are bromine ions. If these ones are substituted by chlorine, what you change is the exchange path between these two coppers. So what you get is a random exchange system. So it's not a random potential. You do not put a magnetic field local on the spin, but you have a random exchange material. Since the material is under an external magnetic field, it doesn't make a big difference. It would only make a big difference at 0.
The Bose glass phase, you said it has finite compressibility?
Yes.
And superfluid density was 0.
The superfluid average order parameter would be 0 in 1D anyway.
Not the order parameter, the superfluid density, the superfluid stiffness.
So the superfluid stiffness
Is 0. And can you say what the resistivity?
that's a good question. That's much more complicated proposal because then it has to be done at finite temperature, and then we go to a certain number of issues. First, theoretical on this related to many body localization or not. But even if I say I'm in presence of the thermostat, which is certainly for this system correct, computing the resistivity is difficult. At least we had some calculation with Thomas Natterman and Pierre Ledussalle, then we find variable range of it. Exponential of 1 over square root of it.
With what?
Dependent on interactions and the parameter. So the Luttinger parameter, the velocity is entering in the exponent. And it's low. I can show you that.
So in the light of time, we should continue with our next speaker. Let's